For the cubic function shown here, I'm going to be performing the first derivative test. I'll be looking for extreme points, which will be a local minimum and a local maximum. After that, I'll perform the second derivative test, in which I'll be looking for a point of inflection. First, let's find the first derivative of this function so that we can perform the first derivative test. The first derivative is going to be 3/2 x squared minus 7x plus 6. Now we'll want to set that equal to 0. But we'd rather get rid of the denominator here if possible. So I'm going to multiply both sides of the equation by 2, which is a nice trick for getting rid of that denominator. We'll have 3x squared minus 14x plus 12 equals 0. Okay, now that's not going to factor nicely by the looks of the graph there. We're not going to get integer zeros out of that. So I'm going to use the quadratic formula, which will help us find the location of the zeros. It's negative b plus or minus the square root of b squared minus 4ac all over 2a. A refers to the first coefficient here, the 3. It's the one that's attached to the x squared. B refers to the negative 14 that's attached to the single x. And C refers to the constant, which is alone. So I'll just write those down. A equals 3, B is negative 14, and C is 12. Let's use that. And with that, we'll find our critical values. All right, if we simplify this a little, we'll get 14 plus or minus radical 52 over 6. And we can pull out the perfect square inside 52. There's a 4 in there, so let's pull that out. It'll become a 2 once it comes out. So we'll have 14 plus or minus 2 radical 13 over 6. Then we could just reduce. And yeah, we'll get x equals 7 plus or minus radical 13 over 3. So those are going to be our critical values there. There's one right here. That's 7 plus radical 13 over 3. And we have another critical value right here. 7 minus radical 13 over 3. They are our critical values. And now we want to do the first derivative test to show that they are extreme values as well. In order to do the first derivative test, just make a line representing your x-axis. we want to clearly mark on there where our critical values occur. So this is 7 plus radical 13 over 3, 7 minus radical 13 over 3. These are places where we know that the derivative is going to have a sign of neither negative nor positive. It's going to have a value of 0 there, because they are, as we can see in the graph, a local max and a local min. Okay, our next step would be to arbitrarily pick several x's that we want to test. It's up to us what we pick. We could pick, for example, -2. Anything to the left of our critical value will work, because we didn't find any critical values over here, which means that whatever the sign is at -2, that's going to be the sign for the derivative everywhere to the left of that critical value. We could try an x of 2 as well, something in between the critical values, and then let's just try perhaps a 6. All right, so I want to find f prime of -2. Let's put in here f prime of 7 minus radical 13 over 3 just for fun, even though we do know what it is. We'll put in f prime of +2, and then an f prime of 7 plus radical 13 over 3. And let's find an f prime of 6. Great. So I want to go back to the original derivative formula. That would be right up here. And I want to plug in the different x values. So let's do 3/2 -2 squared minus 7 times -2 plus 6. See what we get for that. I get 26. Now, since that's positive, we want to come down here and just put a plus there. The derivative at our critical point here, well, we already know that's going to be 0. I don't have to plug it in to know that. F of 2 will be 3/2 2 squared minus 7 times 2 plus 6. Okay, I get a -2 there. Our derivative at the other critical point also be 0. And then finally, our rightmost x that we're testing is an x of 6. Comes out to 18. All right, so we found a negative sign between the critical values, and we found a positive sign to the right. If we wish, we can go ahead and fill in the entire region here. It's all going to be uniform, between the critical values. And now we can just interpret the results of our test. So according to our test, we have a positive slope to the left of the critical value of 7 minus radical 13 over 3. Okay. Then we have a negative slope between the critical values, according to these negatives here. And then on the right, we have a positive slope. Now, since the slope changes from positive to negative at this critical value here, that is proof that we have a local max there. And the fact that the derivative goes from negative to positive at this critical value, that proves that we have a local min at that point. All right, so what are we going to do in the second derivative test then? In the second derivative test, we find a second derivative and set it equal to 0. We're going to solve for the possible locations of the inflection points of the original graph. Places where the second derivative is undefined could be potential locations of the inflection point as well. So we're looking for either type, where the second derivative is 0 or the second derivative is undefined. And we'll do the same thing we did with the first derivative test. We want to analyze the changes in sign in the second derivative. If the sign of the second derivative goes from positive to negative, then we have an inflection point. If the sign goes from negative to positive, we also have an inflection point. But if the sign doesn't change, that's an indication there's no inflection point there. Okay, let's try it on another page here. Our original function was 1/2 x cubed minus 7/2 x squared plus 6x. We had found that the first derivative was 3/2 x squared minus 7x plus 6. We now want to go on to find the second derivative. It's going to be 3x minus 7. In the second derivative test, you set the second derivative equal to 0. So let's do 3x minus 7 equals 0. Okay, we'll solve it. Divide by 3, divide by 3. X equals 7/3. Okay. So this is considered a possible location of an inflection point. For the original graph. In order to prove that it really is an inflection point, though, we want to make a chart like before. We have our x values on this horizontal line. There is one possible location of an inflection point at 7/3. So we already know when it comes to the second derivative that the sign of it is neither positive nor negative there. It's going to be 0 there. Now we simply need to test one value to the left and one value to the right of 7/3. So I'll pick just 0 and perhaps a 4. All right, let's find out if it switches sign. So f double prime of 0. Let's find f double prime of 7/3, and we'll find f double prime of 4. It's going to be 3 times 0 minus 7, which is negative 7. So let's go ahead and put a negative there. In fact, we can just put negatives all throughout that region. The second derivative at 7/3 is going to be equal to 0. That's what we found above. And here, we'll plug in a 4. And we get a positive 5. So we have a positive sign over here. So here we see f double prime is greater than 0. Over here on the left, we see f double prime is less than 0. And this is the cutoff point. So we can say now that there must be an inflection point at x equals 7/3 for the function f of x. Okay, so that's great. And what we'll want to do next is let's find the locations of the maximum in the graph, the local max, and let's find the location of the local min, and let's find the location of the inflection point. So what I mean by that is, if you look back here, we know the x location of the local max, and we know the x location of the local min, but we don't know how high they are. We don't know what they are in coordinate form yet. So in order to do that, we're going to want to plug those x values into the original function. Also, there's an inflection point here too. And it occurs at 7/3, which is right about here, between them 2 points. That's the inflection point. We want to give coordinates for these things. All right, we'll do it on this page. We're going to want to find f of three things. F of 7 minus radical 13 over 3. That's going to be the local max height. Okay. We're going to want to find f of 7/3. That's going to be the inflection point height. And we should find f of 7 plus radical 13 over 3. That will be the local min.